So, good morning students, welcome to the next lecture of biomolecular spectroscopy. If you remember, we were discussing circular dichroism, right. So, now we already discussed the basic concepts of circular dichroism. Now, we are going to deal little bit more into experimental aspects, what are the variables like how sample concentration should vary, what will be the like a limiting sample concentration, what is the cell path length, what is the solvent effect. So, all those practical consideration in this lecture we are going to look into it. So, this is busy slide, but I will walk through in a simpler way, so that we get into the each concepts of that, right. So, if you remember circular dichroism, what we measure basically differential absorption of left and right circularly polarized light. So, we had circularly polarized light, right one right like this and left one like this, right. And we measure a molecule which is chiral, how much it absorbs the left handed polarized light and right handed polarized light. So, that is delta A equal to delta E C L, right. So, delta is difference in molar reactivity, concentration and path length by a chiral molecule. Now, that is what we measure in CD. So, what we need to optimize is concentration, how much concentration we need, so that it is not saturated, what kind of path length we choose, and what are the solvent which are essential for obtaining the high quality and reproducible structural data. You remember in biophysics you have to get the data reproducible, right. Each time if we use same parameter, our spectra should come same, right, that is a reproducible data. So, concentration path length design, how we do that. So, suppose we want to determine the secondary structure of a protein, right, secondary structure of a protein, we have to typically take a concentration of 0.1 mg per ml and the path length of that cell should be 0.1 mm for far UV. Now, you remember in far UV what are the chromophores? The chromophores are amide bond, right, CONH, and that is pretty abundant in the protein. But when we are measuring the tertiary structure like a near UV, then we have to jack up the concentration, because only 3 amino acids are contributing to that. So, typically we require 1 mg per ml with 0.1 mm path length for concentrated sample. So, you require here a relatively diluted sample, you require fairly concentrated sample for near UV CD. Yeah, so this is again can be also for UV. So, if we are decreasing the path length, here 0.1 mg for concentration, here 1 mg in like a smaller path length. But for near UV, as I was saying, only 3 amino acids are contributing. So, one can have even higher concentration like 0.5 to 2 mg in 1 to 10 mm cell, right. So, cell should be thicker, because delta E also depends upon the concentration and path length. So, weaker aromatic signal, we require more sample, more path length, and that has a inverse relationship equal to C1 L1 equal to C2 L2, and that enables the flexible design while obtaining the signal strength, how much signal we need, a sufficient signal to randomize we need. So, either we have to increase the concentration or we have to increase the path length to obtain that decent signal that we are talking about. After like playing with the concentration of path length, we have to check one important experimental condition, that is high voltage. So, if you measure CD, you get a CD signal, and how much your signal is getting saturated, that is given by this high voltage. So, if excessive absorption happens, then your high voltage increases from 600 to 700 volt. Now, after this data becomes noisy, signal to noise goes down. So, you have to keep an eye on the high voltage, and we have to like keep it low, so that it does not produce the noisy data, right. So, for like any absorption at any lambda should be equal to 1 to 1.2 for reliable measurement. So, we have to monitor the HT voltage in real time, and if HT voltage is increasing, either we have to decrease the concentration or we have to decrease the path length of that, right. So, that is about the experimental condition. The third comes the solvent effect. What kind of solvent we should choose, right. You remember we are measuring in the UV, far UV or near UV, and buffer may have some chromophore which absorbs. So, what we have to detect, what we have to get rid, a buffer should not be that itself starts absorbing in this range. So, buffer choice dictates the wavelength axis, what kind of buffer we should have, water, phosphate buffer, and that should can reach up to approximately 190 nanometer. Like some of the buffer which has like a hips or trees, what happens that these guys starts absorbing below 200. So, we have to many times avoid this. Solvent polarity effects n to pi, like n to pi star transition, and that can shift the band. So, essentially we have to avoid all such buffer which can absorb here. So, and the important parameter that we have to maintain the identical condition for a comparative study. So, if you are doing any study where we want to look at the protein only, we should not change buffer, buffer should be always same. Now, sometimes the denaturation, when we looking at the protein stability study via folding mechanism, so sometimes denaturation we have to do, like we take urea 0 to 8 molar, guanidinium hydrochloride 0 to 6 molar, these guys actually also starts absorbing at a lower wavelength, like a, so sometimes you have to cut it your spectral window in far UV region, right. So, why we do that? The unfolding study we want to measure the delta G and M value, and sometimes we also use TFE for probing the helicity that can be protein produce. So, these are some of the denaturants and perturbants that we use, and we have to only take care that it should not absorb. So, right, that is the one of the important part. The another one, aggregation. So, when protein aggregates, light scattering can happen, and that can distort the spectra and elevates the high voltage. So, basically dynamic light scattering one can do it before looking at what is actually if your protein has aggregates or no. So, we have to get a monodispersed sample, otherwise we centrifuge it or filter it to get rid of all these aggregated species that may be in our experimental sample. And finally, this CD is extensively used in biopharma, where suppose we are doing the high concentration monoclonal antibody, which is typically formulated say 10 to 100 milligram per ml. It requires ultra short cell, right. So, ultra short cell, very thin cell, because you know concentration here we discussed here, concentration and path length are kind of constant, that should be constant. So, if our concentration is high, we have to decrease the path length in the lower wavelength band. And when we are doing biosimilar study, we want to prove that this one molecule and the another molecule that we are making in our lab or the industry, both are same, that is called biosimilarity assessment. It demands that secondary structures should be very matching. So, less than 10% it should be, and the Tm should be less than like a 0.2 centigrade, Tm is melting temperature. So, that kind of application also is feasible using CD spectroscopy. And so, coming back to the basic concepts. So, we know this also CD is fundamentally absorption based. Here we measure circularly polarized light. So, it governs by this Beard-Lambert's law of total absorption and differential absorption. So, AL is left polarized light, EL, CL and RAR is right handed circularly polarized light. So, differential absorption one can given by AL minus AR, and that will be molar absorptivity difference, concentration and length. Now, this is called molar ellipticity because we are differentially the molecule is differentially absorbing right handed and left handed circularly polarized. So, because of that whatever comes is elliptically polarized, one axis is more absorbed than other, and this is called molar ellipticity. So, molar ellipticity can be given that in terms of theta, theta will be theta by 10 CL degree, like a this is measured in a degree, and these are the decimole per CD optimum, and that is what now we can also explain this molar ellipticity by mean residue ellipticity of protein. So, we just want to factor it, how many residue it has, what is the concentration. So, all those we can factor it and it becomes per residue, right. So, we design the principle, choose such that C, L and molar concentration is taken into factor, and then CD one rather than the molar ellipticity we can even explain in terms of mean residue ellipticity for a protein, right. So, practical range for concentration and L for a protein when we are doing CD spectrum. The rule of thumb for design of Beer-Lambert constant, that our target absorption should be 0.5 to 1, after that it becomes non-linear. So, most absorbing wavelength that we are looking at, like say in this range 190 to 200, this should not cross basically more than 1. So, for far UV region, so like 180 to 200, the cell path length should be 0.01 to 0.1 mm, and protein concentration should be 1 to 2, and sample volume we require just 5 to 20 microliter. So, very high absorption by peptide bond that occurs in this cell, and we require a very short cell. If you move little bit more, right, in the range of 200 to 250, the cell path should be 0.1 to 1 millimeter, and concentration you can like a decrease 0.1 to 1 mg, and volume you require more 300 to 500 microliter. This is commonly used for secondary structure analysis. Then in near UV, right, which is typically used for tertiary structure, you require a thicker cell, that is up to 1 centimeter, and protein concentration up to 2 mg, and then you require more volume because now cell is thicker, 1 to 3 ml, and here the chromophores are aromatic bonds, right, those are weak, and you require longer path length, high concentration. Finally, visible CD like a heme and other chromophore, you again require a thicker path length, slightly lower concentration, and volume is 1 to 3 ml. So, this essentially why we are requiring lower concentration, because large molar reactivity, and that can lower the concentration, right. So, these are some of these typical concentration and path length and the volume that will be required for doing CD experiment. JASCO, which is one of the prominent CD manufacturing company, that has a recommendation that the far UV secondary structure should be 0.1 mg per ml in 1 ml cell, provides a robust spectrum, and 1 mg per ml should be used with 0.1 mm cell to keep absorption roughly equal to 1, right. Now, there is a academic guideline that has come up, so which says concentration is inversely proportional to path length. 1 mm cuvette requires 10 into C of a cm cuvette for the same absorption, So, essentially the C1 L1 equal to C2 L2. So, if you reduce the path length, protein concentration should be more. That is what Harvard guideline says, and this is JASCO guideline says, right. So, how now you measure, how you design quantitatively for far UV protein CD. So, it is a design problem, as the rule of thumb is we want our absorption not more than 1, right, and we want to keep this concentration and path length so that it does not go beyond 1. So, how we design, what kind of concentration and path length we have to choose. So, we are measuring say far UV CD something around 190 to 250 for a protein. Suppose our protein is 50 kilodalton and expected mean residue ellipticity at 222, because the CD in CD signal you get a alpha helix basically. So, here the theta mean residue at 222 is 30,000 degree centimeter square decimole square for 100% helix. This is the reference you can choose. So, choose a path length of 0.1 cm, that is 1 mm. Choose the concentration of 0.1 mg, right, per ml or 0.1 gram per liter, and mean residue weight is about 110 Dalton. So, mean residue ellipticity one can measure is theta MR is MRW into theta by 10 CL, right, or you can rearrange theta should be 10 CL by mean residue weight into theta MR, and you can calculate this concentration, put the mean residue weight, that is 110, you can find it out theta MR equal to 30,000, right. So, this gives, if you do little bit of mathematics, this gives the signal amplitude of 20 to 30 millidegree, and that is within the dynamic range of the above noise. So, typically that is the concentration one need to take to find a robust CD signal, and that is the quantitative design example for far UV CD, right. Now, again emphasizing on concentration and path length, how we are trading off in a design map. So, we know that delta A is equal to delta E CL, delta A is like a differential absorption of left and right handed polarized light, delta E is difference in molar absorptivity, concentration and the path length. For a fixed signal, we can have the trade off between C and L inversely, like C1 L1 equal to C2 L2, right, that is what we saw it. So, the design rule is one must work 10 times higher concentration, that for example, limited solubility or formulation concentration, and reduce 1 by like a 10x to maintain a similar absorption. For an example, here if you look at very pure protein, one can easy dilution, one can have 0.1 gram per ml for a path length 1. Very high concentration of formulation, say biologics, which is concentrated up to 1 mg per ml, you can have a path length of 0.1. A very high concentration, suppose MABs, this is this is formulated at say 10 to 50 mg, you can have even path length lower than 1/10 of that or even more than that. Short path length, you can have a demountable cell, and this basically compatible with the formulation. And for near UV tertiary CD, you have to have slightly higher concentration, 1 mg per ml, path length should be 10, because here why we are doing this, because here we are getting weaker signal coming from the aromatic. So, the rule is concentration is inversely proportional to the path length, that is what. So, concentration decreasing, path length increasing, concentration increasing, path length decreasing. So, typical volume for 300 microliter 1 mm cell versus 3 ml of volume of 10 mm, right, path length. So, that is the design principle for concentration and path length one can have. Now, another important aspect that I discussed with you is the HT voltage, right. So, if you measure this, you get two signal, one is for HT voltage which can decrease, and one you get it decrease like this, and you get a CD signal something like this, right. So, HT voltage basically should not exceed more than 600 volt. So, and where the HT voltage is coming from? This absorption that is happening in the CD signal of a protein or buffer, right. So, the sample plus buffer plus cell, all these three can saturate the signal. Therefore, one has to be really careful with the HT voltage. So, CD instrument basically monitors this high tension voltage, it is coming on the like a PMT, and that approximately detects how much light is going. So, say many system it starts warming, that if your HT voltage is going more than 700, 600 or 700, you are saturating your signal. So, at high HT you have too few photons at the detector, that gives you noisy signal. So, essentially rule of thumb that you should not increase your HT voltage more than 600 to 700 volt. So, therefore, we have to keep right your absorption at any lambda not more than 1 or 1.2, right. So, otherwise your HT voltage will spike and you are starting getting the noisy sample, and that can truncate the data at that wavelength. So, really noisy, very noisy data you start getting, rather than this smooth curve you start getting some noisy data which you do not want to have. So, a mechanistic note is at high absorption, the noise in delta A is amplified relative to the signal, and lock-in detection cannot be fully compensated if the fundamental photon shorts the the detector. Therefore, at any wavelength where absorption is going more than 1, you have to reduce the concentration, reduce the path length, and bring the HT voltage lower so that we can detect it. That is all about the HT voltage. So, we discussed about concentration, we discussed about path length, we also discussed about how much HT voltage we should have. Now, the third and another important aspect is what should be the consideration for solvent and buffer, and what will be the spectral window that we are talking about, right. So, solvent choice is very important, right. All the protein comes in some or other solvent. We do not want to mess up too much with the formulation buffer or the solvent or the buffer that we are using, but unfortunately some component of these formulation buffer can also absorb in this UV light. So, general requirement for doing CD experiment, what we want, the sample must be soluble and structurally stable, and for keeping it soluble and structurally stable we require some solvent or buffer, right. But solvent must be optically transparent, right, it should not reflect or something like that. In the CD range that we are talking, it should be optically transparent, and mostly your solvents should have a achiral molecule that should have a negligible CD, because what we want to get a signal from our protein molecule, not from the buffer molecule, right. So, that should have the achiral nature. We do not want these molecules to be chiral. The molecules means component of buffer should not be chiral, right. So, we want to avoid all sorts of background noise. Therefore, the transparency limit is absorption should be much less than like 1 per cm. So, buffer solvent concentration we can have water and very dilute NaCl. We can, like, if we have this, even we can go to 170 to 180. So, extremely good solvent for UV with low ionic strength. The phosphate buffer, which is one of the popular buffer for protein, can tolerate 10 to 50 millimolar, and here we can even go up to 90, right. So, it is a widely used and moderate absorption that we have. Then comes the tris or HIPS buffer. Many proteins are stable in this tris buffer and HIPS buffer, that can go as low as 200 to 25. But lower than that, you see, if you remember, lower than that there are some positive signal coming from beta sheet and alpha helix, that will be difficult to see. So, this limits the far UV region, right, 180, 190, we cannot go in HIPS and tris buffer. If you have a imidazole, right, many proteins are eluted with imidazole. If imidazole is there more than 150 millimolar, it starts absorbing more than 205, and this has a stronger absorption, can distort the spectrum. And if you have a glycerol or sugar that is high, more than 200, it again absorption increases, and other than that the viscosity of the molecule increases. So, now molecule will not be tumble. And if you have a common organic solvent like methanol, ethanol, ACN, then you can go up to 190, and this is often used for a small molecule, but not for far UV for peptide, because these are not very compatible solvent for peptide. So, for an example, if you are taking a lysozyme which is 15 kD protein, 50 millimolar phosphate buffer at pH 5 gives a clean far UV CD, but if we add 150 NaCl or imidazole, it visibly distorts the CD signal in the region 190 to 200, and that is because of solvent absorption or scattering. So, we cannot, if you remember, we cannot go high in the salt concentration or pH, otherwise our distortion in the spectrum and scattering starts happening, right. So, that is the solvent effect of amide transition. So, you remember we are talking about the far UV absorption. Far UV absorption, our chromophores are these amide bond, amide transition. So, here we have a pi to pi transition that happens around 190, and basically molar absorptivity is 7,000 to 10,000, that is a electronically allowed. Now, we can have a relatively sensitive solvent, insensitive this transition, this will not affect too much. So, this dominates the far UV region, CD signal comes mostly in this. Now, another comes in N to pi transition, which is around 250 into 222, and this is electronically forbidden transition. Therefore, you see the molar absorptivity is less here compared to this one. Now, this is strongly solvent sensitive. So, it involves the lone pair and carbonyl oxygen. If you remember, we are talking about CONH, right, that is the. So, one is N to pi and another is pi to pi star, right, and N to pi star. So, this one is here and this one is here. Now, in the CD signal, if we are talking these two, so here we are talking that this is impacted by solvent. So, it involves lone pair on carbonyl, and also CONH2 hydrogen bond can affect it, right. So, this is the transition we are talking about. Pi to pi star, it is a allowed transition, N to pi star, it is a forbidden transition, but happens it is a weaker, this is a stronger one. A peptide N like a is a chromophore, that is what we have, two bond. So, solvent can affect on the amide transition. How it happens? It can form the hydrogen bond. So, if you look at NHCO, it can form the hydrogen bond with H2O. If hydrogen bond are formed, that means lambda can shift by 2 to 3 nanometer, and your this absorption for the CD signal can change by 10%. If it is forming the hydrogen bond with organic solvent that forms the weak hydrogen bond, the lambda can shift by 1 nanometer and the molar absorptivity can shift by 10%. And if it is in high salt, the lambda can also shift by 1 to 2 and this is by 10 to 15%. So, hydrogen bonding can stabilize the n orbital and therefore, it raises the N to pi transition towards blue shift. So, it can come lower, right. The polarity or dielectric constant, if you are changing the salt, it shifts the energy gap between N to pi orbital, and electric field, if we change the buffer component like imidazole or salt, that can also modify. And protonation state like pH can protonate or deprotonate the ionizable proton, and therefore, that can also affect. So, look at the solvent has a tendency to change the absorption of the CD signal. Therefore, the effect of solvent on the protein structure can be easily understood by looking at how the absorption signal is getting perturbed by the CD, and that is what is basically used to understand what is the best solvent for a CD. So, that is what happens. So, solvent can change, solvent suppose we change from water to TFE. TFE, if you know little bit of biochemistry, it is known to change the secondary structure of a protein. A disordered protein can take the helix. So, what happens when you add the like a change water with a TFE, it can shift the N to pi star transition by 2 to 5 nanometer, and therefore, CD amplitude can change, and therefore, apparent change in the solvent environment that is reflected, and the critical point always you compare with identical solvent condition. So, what it changes TFE pi to pi star, here it changes the low sensitivity, but N to pi star is a high sensitivity, and because of this lone pair that we have. So, this basically changes. So, critical point is N to pi star transition 10 to 100x more solvent sensitive than pi to pi star. So, if you change your solvent, this signal is very, very critical, right. 215 to 222 is extremely critical. Now, how do you minimize the solvent interference? What we should do and what we should not do. So, we use the low concentration of buffer as I discussed, like a 5 to 20 millimolar phosphate or acetate. We should have non-absorbing, like we should not have NaCl, KCl at a minimal very high concentration. This can also change the dielectric constant. and then we should actually filter all the solution, so that we do not have a bigger particle, right. We should remove the oxygen, dissolve oxygen, you said this sometimes work as a quencher. So, degas the solution, remove the dissolved oxygen, and you use the ultra, like a high quality, ultra high quality quartz cuvette, right, far UV grade, and then match the buffer baseline. Always take buffer as a reference, so that you do not have much HT voltage and CD signal coming from there, and you absolutely let the temperature be equilibrated. So, on the instrument, let the pass nitrogen gas for some time, let it equilibrate, and then you can start taking the signal. Now, what you should not do, you avoid strong absorbing buffer like a tris, hips, imidazole and all those. Always avoid the high concentration and aromatic additive like a DTT and all those. Never use regular glass or acrylic cuvette, that is not compatible with CD. So, just ignore that, you use only quartz, right, and do not ignore the baseline HT voltage. Always you have your Lakshman Rekha is 600 to 700 voltage, do not cross that, that will distort your spectrum, and avoid buffer with high glycerol or sucrose concentration if we are doing far UV, right. So, these are some of the practical considerations that we have to take care when we are measuring the CD. With this, let us end it here today, and we look forward to have some more practical aspects of measurement of CD and how we can use the CD for secondary structure determination in the next class. Thank you very much.